Chapter 6 Transactions. Transactions are signed messages originated by an externally owned account, transmitted by the Ethereum network, and recorded on the Ethereum blockchain. This basic definition conceals a lot of surprising and fascinating details. Another way to look at transactions is that they are the only things that can trigger a change of state, or change a contract to execute in the EVM. Ethereum is a global singleton state machine, and transactions are what make the state machine tick, changing its state. Contracts don't run on their own. Ethereum doesn't run autonomously. Everything starts with a transaction. In this chapter, we will dissect transactions, show how they work, and examine the details. Note that much of this chapter is addressed to those who are interested in managing their own transactions at a low level, perhaps because they are writing a wallets app. You don't have to worry about this if you're happy using existing wallets applications, although you may find the details interesting. The structure of a transaction. First, let's take a look at the basic structure of a transaction, as it is serialized and transmitted on the Ethereum network. Each client and application that receives a serialized transaction will store it in memory using its own internal data structure, perhaps embellished with metadata that doesn't exist in the network serialized transaction itself. The network serialization is the only standard form of a transaction. A transaction is a serialized binary message that contains the following data. 1. Nonce, a sequence number issued by the originating EOA used to prevent message replay. 2. Gas price, the price of gas in Wei the originator is willing to pay. 3. Gas limit, the maximum amount of gas the originator is willing to buy for this transaction. 4. Recipient, the destination Ethereum address. 5. Value, the amount of Ether to send to the destination. 6. Data, the variable length binary data payload. 7. V, R, S, the three components of an ECDSA digital signature of the originating EOA. The transaction messages structure is serialized using the recursive length prefix, RLP encoding scheme, which was created specifically for simple byte-perfect data serialization in Ethereum. All numbers in Ethereum are encoded as big-endian integers of lengths that are multiples of 8 bits. Note that the field labels are shown here for clarity but are not part of the transaction serialized data, which contains the field values RLP encoded. In general, RLP does not contain any field delimiters or labels. RLP's length prefix is used to identify the length of each field. Anything beyond the defined length belongs to the next field in the structure. While this is the actual transaction structure transmitted, most internal representations and user interface visualizations embellish this with additional information derived from the transaction or from the blockchain. For example, you may notice there is no from data in the address identifying the originator EOA. That is because the EOA's public key can be derived from the VRS component of the ECDSA signature. The address can, in turn, be derived from the public key. When you see a transaction showing a from field, that was added by the software used to visualize the transaction. Other metadata frequently added to the transaction by client software includes the block number and a transaction ID. Again, this data is derived from the transaction and does not form part of the transaction message itself. The transaction nonce. The nonce is one of the most important and least understood components of a transaction. The definition in the yellow paper reads, nonce, a scalar value equal to the number of transactions sent from this address, or in the case of accounts with associated code, the number of contract creations made by this account. Strictly speaking, the nonce is an attribute of the originating address. That is, it only has meaning in the context of the sending address. However, the nonce is not stored explicitly as part of an account state on the blockchain. Instead, it is calculated dynamically by counting the number of confirmed transactions that have originated from an address. There are two scenarios where the existence of a transaction counting nonce is important. The usability feature of transactions being included in the order of creation, and a vital feature of transaction duplication protection. Let's look at an example scenario of each of these. 1. Imagine you wish to make two transactions. You have an important payment to make of 6 Ether, and also another payment of 8 Ether. You sign and broadcast the 6 Ether transaction first, because it is the more important one. And then you sign and broadcast the second, 8 Ether transaction. Sadly, you have overlooked the fact that your account contains only 10 Ether, so the network can't accept both transactions. One of them will fail. Because you sent the more important 6 Ether one first, you understandably expect that one to go through and the 8 Ether one to be rejected. However, in a decentralized system like Ethereum, nodes may receive the transactions in either order. There is no guarantee that a particular node will have one transaction propagated to it before the other. As such, it will almost certainly be the case that some nodes receive the 6 Ether transaction first and others receive the 8 Ether transaction first. Without the nonce, it would be random as to which one gets accepted and which rejected. However, with the nonce included, the first transaction you sent will have a nonce of, let's say, 3, while the 8 Ether transaction has the next nonce value, 4. So that transaction will be ignored until the transactions with the nonces from 0 to 3 have been processed, even if it is received first. Phew. 2. Now imagine you have an account with 100 Ether. Fantastic. You find someone online who will accept payments in Ether for a McMuffin widget that you really want to buy. You send them 2 Ether and they send you the McMuffin widget. Lovely. To make that 2 Ether payment, you sign a transaction sending 2 Ether from your account to their account, and then broadcast it to the Ethereum network to be verified and included on the blockchain. Now, without a nonce value in the transaction, a second transaction sending 2 Ether to the same address a second time will look exactly the same as the first transaction. This means that anyone who sees your transaction on the Ethereum network, which means everyone, including the recipients, or your enemies, can replay the transaction again and again and again until all your Ether is gone, simply by copying and pasting your original transaction and resending it to the network. However, with the nonce value included in the transaction data, every single transaction is unique, even when sending the same amount of Ether to the same recipient address multiple times. Thus, by having the incrementing nonce as part of the transaction, it is simply not possible for anyone to duplicate a payment you have made. In summary, it is important to note that the use of the nonce is actually vital for an account-based protocol, in contrast to the unspent transaction output (UTXO) mechanism of the Bitcoin protocol.